Right, thanks very much. Yes, morning everyone. So this is actually a continuation of the talk that I gave 5 years ago, I think it was when we were here. The work's been delayed a number of times. The good delays were because Sarah, who was working on the project, had time off on maternity. That's a nice reason for delay. And there's also been a number of not very nice reasons for delays, which I'm happy to tell you about in the pub, but I won't grumble about them now. So the work is somewhat further on than it was, but it's not 5 years worth of progress, certainly. So this is a problem that's intrigued me for a long time. It's a very, very simple problem that most of the time if you want to approximate something is easy. You want to approximate an integral, yes, piece of cake. But Wiener-Hopf equations and Wiener-Hopf problems seem to just be an outlier. They really don't like being approximated. And if you were to try with just a boundary value problem and say, okay, well, I'll just, lob this at some big fem code or something. The problem is, as we all know, that it's the intricate connection between near and far field effects. Very, very hard to capture numerically. It can be done, but it's very hard. Or, if you do the sort of approach that I like to do, where you kind of go as far as you can, analytically, you get to a Wiener-Hopf equation, and you try to approximate the solution to that, of course, it's the connection between the singularity structure in the finite part of the plane and the behavior at infinity. And if any of that gets messed up, then the approximation will just be rubbish. So any sort of local approximation can break those. And 5 years ago, I talked about a problem in diffraction in Mindlin plates, where it just had finite branch cuts, but it had a very nasty kernel. And I want an approximate solution to this Wiener-Hopf equation. And I found a way to do it, which is it's somewhat crude, but fairly generic. And so I thought, okay, well, could I make something, particularly, can I make a library that gives you a solution to arbitrary Wiener-Hopf equations? Well, that's a very dangerous thing to say. At least some Wiener-Hopf equations. So that's kind of my goal. The main use is the one that I started out with, which is if you've got some horrible kernel that comes from something like elasticity, it's going to be a mess. The one from Mindlin theory was a mess. There are worse ones. Can you just have an approximate solution to the Wiener-Hopf equation? Not too much work. Just an approximation. Like I say, in most problems, that's easy. If you just want a quick and dirty approximation to most things, you can do it in 5 minutes. Also, it might be handy if you have some very clever method for a specific problem, and you maybe having a bit of doubt, thinking, well, is my analysis or my numerics actually doing what I think they're doing? It will be a way to verify. You can at least compare. So that's the goal. Something nice and easy. And ideally, what I would like is that you tell this library what's your kernel, where are the singularities, where are the branch cuts, and then it gives you the approximation. Of course, in real life, Wiener-Hopf problems are never like that. There's always some booby trap in every single problem. There's something nasty waiting for you. But that's the sort of ideal goal. Okay, so this is how I do it. So just a generic Wiener-Hopf equation. It can be scalar, it can be matrix. Obviously, if it was scalar, I wouldn't do this, although I will show a few results for scalar problems just to demonstrate this thing works. But obviously, a scalar equation you can just solve. But start with any typical Wiener-Hopf equation, kernel, unknown functions with known domains of analyticity, all the standard notation. And I'll put unknowns in red just to make it more obvious, easier to see. And okay, so basically I want an approximate solution to this. And the way I did for this implicit quadrature scheme for this problem with finite branch cuts was that I just said, okay, well, the first step is I know I could represent my unknowns as integrals around the branch cuts. Cauchy's integral formula, very standard thing. Here I'm trying to do it with infinite branch cuts, so it's kind of the next step up. Okay, so this isn't an approximation, this is just a general statement that the unknowns could be represented as Cauchy integrals. And again, these diagrams are very generic structure where you've just got branch points of plus or minus k. You can have something more complicated than this. You can have multiple branch points and branch cuts. And I'll say something more about poles shortly. Okay, and although we don't know what these functions are, you do at least know their singularity locations. That comes from the Wiener-Hopf equation itself. So you can say what the you can say where the singularities are, what your path's going to look like. And there's one more thing you can say, which is that if everything goes to 0 at infinity, oh yeah, of course this is another thing I should emphasize. These representations, these are global formulae. What they're saying is if you knew your function on the contour, then you know it everywhere. It's an important point, which I'll come back to. So if you knew A plus on this contour going around the branch cut in the lower half plane, then actually you would know A plus everywhere, and likewise R minus. Of course, we don't. Okay, it would be.
Omegas, they are domains or?
No, they're the contours.
The contours.
Yes. So the contours going around the singularities.
The contours.
Yes.
But how this integral defined A plus on the contour? So there is a singularity on the contour. Yes.
No. The alpha would be somewhere inside.
No, but A plus is a function of alpha. And
yes.
So you are saying that these are global representations are A plus on omega minus. So alpha is on omega minus in this formula.
No, alpha is anywhere inside.
Okay, but it is written.
So I'm not quite sure I understand the issue. Hopefully it will become clearer. Okay, so the other thing that we know is that if these functions tend to 0 at infinity, then in fact when we let the radius of these things tend to infinity, there'll be no contributions from the arcs at infinity, and you can rig things multiplying or dividing the Wiener-Hopf equation by appropriate factors. You can rig things so that the solution is unique if the unknowns tend to 0 at infinity. So sometimes that just comes out automatically, and other times maybe you have to multiply by a polynomial or divide by a polynomial, something like that, just to tweak the behavior at infinity to make sure that if you say, okay, well my unknowns tend to 0 at infinity, that corresponds to giving you a unique solution from the same sort of thing as you would have from the tip condition. Okay, and then the next thing is, so well let's just imagine I was in an ideal world. If I did know what these functions are.
Sorry, very last time I interrupted you. I'm sorry. Again about this formula. So of course I can understand that we can say alpha when alpha is on omega minus, then integral on the right is understood as alpha plus as the limit from
okay. Oh, so
domains. That's fine.
Right.
But then of course the integral would define everything everywhere, but automatically inside on the minus side of omega minus is going to be 0. So integral is 0. So integral only because A plus is analytic outside. So when you put alpha inside, then it is 0. Is it not?
No, it's not 0 because its value would be the residue at z is alpha, wouldn't it? So it just says that A plus of alpha is A plus of alpha.
I promise to interrupt you last.
Okay.
So
right. So in an ideal world, if I did know what these functions were on the faces of the branch cut, what would I actually do to calculate it somewhere? Well, I'd have to use quadrature. Wouldn't have a choice. Okay. So if I knew it along here, and I knew the other function along here, the only way I could actually calculate it out here, or the only obvious way at least, would be to use a quadrature formula on these contour integrals. So okay, let's suppose we did that. So at the moment we still don't know what these functions are, but let's pretend we did. Okay, so what would it look like? Basically every quadrature formula just says that your integral is approximately the value of the integrand at some points multiplied by some constants and added up. All of them are the same. Doesn't matter whether it's the trapezium rule or the 1531 Gauss-Cronrod pair. They all have exactly that structure. So I can do that to my Cauchy integrals. And what happens, so I'll put some nodes and I'll say a bit about where I put the nodes in a moment, but I put some nodes on the branch cut, and then I can say, well, actually, my plus function is approximately a sum, and so I've still got my 1 over 2 pi I there, and all I'm doing is I'm evaluating the integrand of the Cauchy integral at the appropriate points and multiplying it by the appropriate weights. And the same thing for R minus. So so I still don't know what these things are, but now it's just a discrete set of finite values. Okay, so if I choose my nodes, then what I need are some values, and they're actually just the difference between the values on the right and left hand side of the branch cut, which is what you'd expect because the Cauchy integral goes round. Okay, and this is the only approximation in the whole thing, and the thing that appeals to me about this is that when we solve the scalar Wiener-Hopf problem, say, oh yeah, we can solve that exactly. Well, actually, in the vast majority of them, we have to factorize the kernel using Cauchy's integral formula. And then what do? We use quadrature. We have to. All right, there might be a few where you can do something. Maybe you can actually do the factorization by inspection or some magic trick, maybe the infinite product method that was mentioned yesterday. But in the majority of cases, in a scalar problem, you have to use quadrature. So I'm not doing anything that I wouldn't do in a scalar problem. I'm just doing it in a different order. Okay, so the integrals, the Cauchy integrals, are just going to be replaced by quadratures. And like I said, yeah, the same thing happens in most scalar problems. The difference is, there's not a free gift. The difference is that you know what you're integrating there. Here, I still don't know what I'm integrating. I'm just saying, well, if I did know the function, this is what I would do. Right. Okay, so I still don't know these unknowns, but it is just a discrete set now. And we know that they're related by the Wiener-Hopf equation. And I use this notation subscript S to mean you could be on the left-hand side of the branch cut or the right-hand side. So I'm just going to evaluate my standard Wiener-Hopf equation at a point on the branch cut in the upper half plane. Okay, so when I do that, A doesn't get a subscript S because he's analytic in the upper half plane, and R plus doesn't get a subscript S, same reason. But the things that are not analytic in the upper half plane, they get a subscript S. So there's two versions of this equation, one on the left-hand side and one on the right-hand side. And then I just take the difference between the two versions. Okay, so the right version minus the left version. And what we see appearing, okay, so the R plus here just disappears because he's the same on both sides. We see the same differences that we saw in the Cauchy integrals, this difference between the right and the left value. And then I say, okay, well, I'm evaluating on a point here. I can introduce my Cauchy integral representation for A plus because that's an integral around here, so it should work pretty well. If I'm standing there and I represent A plus as a quadrature around this contour, that should work quite nicely because I'm quite a long way away from the integration contour, so I'm nowhere near this horrible pole. Okay, so now I take my Cauchy integral representation for A plus, which has been replaced by quadrature, and I put that into my equation that I derived from the Wiener-Hopf equation. It looks horrible, but actually it's really rather nice because it's just a linear system of algebraic equations relating the differences as one of the R differences to all of the A ones. And if you do it the opposite way round, so if you go into the lower half plane and evaluate the Wiener-Hopf equation on the branch cut, take the difference between the two sides, put in the quadrature representation for the function that's analytic down there, you get the opposite. You get the other half, if you like, of the linear system. So you get a set of equations which says, okay, you've got one of the A's related to all of the R's, and when you put it together, you get a system of n plus n minus, so that's the number of nodes I use in the upper and lower half plane. That's the number of equations I get, and it determines all of these differences. So then all you have to do is solve the linear system, and you have an approximate solution. It should work. Like I said before, though, I don't want to have to repeat. It's really boring, this analysis. And it's almost the same. Every time you do it, it's the same. I've done it for about 4 or 5 problems. I'm sick of doing this. I just want to do this generally. Okay, so what do I want my library to do? There's essentially 2 things. One is, give me the nodes and the weights. Tell me where I should put them. I don't want to do that. I'm going to tell the library, look, here's the singularities, you tell me where to put the nodes. Okay, and then the other is form the linear system, and I'll say a little bit more about that part in a minute. Positioning the nodes is actually quite, well, somewhat easy. It's a very, very simple trick that basically, if I look in a textbook on numerical analysis, quadratures are pretty much always given in this form. They say, right, if you've got an integral from -1 to 1 of some function, again, it will look like a sum of function values at certain points, multiplied by certain weights, and added up, all of them. And it's very easy, just a substitution, to map that to a section of a complex contour. 5-minute job. Okay, and so you can then say, right, well, I can have a quadrature rule that will work well for a contour integral. Marvelous. So you can start off with some, quite accurate formula. Typically, I use either 7 or 9 point Gaussian rule. No particular, you could use a more or less accurate one. And then you just map those to, you maybe divide your contour up into bits. A very simple linear substitution will give you a set of nodes and weights that will work for those little chunks. Of course, with these integrals that we're doing here, you're probably going to have something nasty going on at the end. Probably something like a square root singularity, maybe something slightly worse, and possibly something nasty at infinity. But you can deal with that as well. And this isn't something I've ever really seen in a book, but it's a very, very simple idea. So in a book on numerical methods, it would probably say, well, if you've got a square root singularity at the end, do a substitution, and then apply the quadrature to the integral after you've done the substitution. But actually, you can look at it in a slightly different way and say, well, let's just suppose I've got this function, and it's got a square root singularity at the origin. What's the substitution I would do? Z is s squared. Okay, do that substitution, it changes to this integral here. And so if this has a square root singularity, the fact that you're now doing f of s squared makes the singularity go away, at least as far as the quadrature is concerned. But a slightly different way to look at it is say, well, actually, you can think about this as just using a different set of nodes and weights. Okay, so the new nodes, so if the old nodes that I would use for an integral from 0 to root epsilon were sj, then the new ones are just sj squared. And if the old weights were wj, then the new ones are just 2 times sj times wj. So basically, you just mess around with the nodes and weights, and the singularity, as far as the quadrature is concerned, just disappears. And you can remove all sorts of singularities doing this. And then there is one slight concern that you might say, well, okay, suppose this has got a 1 over root z. Okay, and if you did it analytically, so if you knew what the function was, okay, so you do this substitution and you get a 1 over z, or 1 over s rather, and that would cancel this s here, and that would be wonderful. But of course, I'm not doing any of this because I don't know what I'm integrating. So there is a danger of a removable singularity at the end. Actually, it's a piece of cake to avoid those, because if you use Gaussian quadrature, you never actually have to evaluate the integrand at the end point. So I just don't need to worry about them. And you can remove singularities at infinity in much the same way, just a simple mapping, and then just think about what does that do to my nodes and weights that I started with. It can all be done by some fairly straightforward subroutines, and so this part of the library works. Okay, you just say to it, look, this contour, these singularities, give me the nodes and weights, and it does. And then you say, right, my integral is just evaluate my function at these nodes, multiply by weights, add them all up. So I do a very quick demonstration. This is a problem that was in a paper by Andy Norris, and I don't know Wang's first name, unfortunately. Basically, it's a scalar Wiener-Hopf problem. They wanted to product factorize this function r, which is just these combination of these two different square root functions. And so the standard thing, you go through the Cauchy integral formula setup, and what you end up with is that you have to evaluate this integral, which is a contour integral from ik to k, and you have your function, the log functions evaluated on one particular face of the branch cut. And so yeah, you have to do this integral. What they did in their paper was they made some substitutions, mapped it into two real line integrals, did some more stuff. I don't remember the exact details, which you can do. But here I'm going to go for something a bit of overkill. This library that I intend to use for cases where I don't know what the integrand is. I'm going to use it for this integral, just to show, okay, that it works. Okay, so I just picked some random values here. I haven't had time to do any detailed analysis of, you know, different errors for different alphas, but just pick a value for k and a value for alpha. Now, if you say to the library, okay, look, I'm integrating from ik to k, and you don't tell it any information about singularities, what you get is basically what you would expect. You get a few significant figures, and then as you double the number of nodes you're using, the error goes down, but it goes down very slowly. And this is exactly what I would expect to happen. But if you tell it that there are square root singularities at the end, it gives you a different set of nodes and weights, and then you say, okay, I'll evaluate my integrand at those nodes, multiply them by the weights and add them all up. You very quickly converge to machine precision accuracy. So it's just a demonstration, like I say, it's overkill. It's not how I would recommend doing a quadrature where you know what the integrand is, but it does work. Okay, so now the other thing that I want it to do is form the linear system for me. I don't want to be going through this analysis of taking differences between Wiener-Hopf equations on different side of branch cuts all the time. And it turns out that there are various different structures of Wiener-Hopf equations when you look at it from this perspective, and the basic one is the one that has one pole due to the incident wave. So your R plus function is just a constant or a constant vector if it's a matrix problem, divided by alpha minus alpha naught. Okay, so now I can't say that A plus is just an integral around a branch cut because it's got a pole. Okay, but what you can do is you can say, well, I'll just write A plus is another vector divided by alpha minus alpha naught plus something which doesn't have a pole at alpha is alpha naught. And you can easily determine Q, just substitute that back into there and match the residues on both sides. And once you've done that, the process then of deriving the linear system of equations is exactly the same for all problems. So I've only do it once, write a subroutine to do it, and then forget about it. Never have to do it again, hopefully. So yeah, any problem that has this structure, so Sommerfeld is the most obvious one, but the Rawlins mixed problem also has this structure. The problem I was talking about with thin plates had the same structure. So any problem where you've just got that simple R plus, it's always dangerous to say any, but hopefully any problem, this will just work. Okay, so again, I've not had time for any in-depth analysis of the errors, but I set it up and I said, okay, right, here's, for the Sommerfeld problem, you've got branch points at k and minus k, you've got square root singularities. So just pick a random angle of incidence, and again, just a random point at the complex plane, try evaluating. And again, we get the same sort of thing as I had with the explicit integration. If I don't say to the library, look, the square root singularities, then you get a couple of significant figures accuracy. But as you double the number of unknowns in the linear system, the error doesn't go down very fast. Again, it's exactly what I would expect. If, on the other hand, you tell it that there are square root singularities involved, the accuracy gets a lot better. So 288 unknowns, which in modern terms is none, because it, you know, even on my ancient tablet, it inverts in a fraction of a second. So yeah, anything less than 1,000 unknowns is effectively none. Now, it's not. I am a little bit perturbed by this. That okay, it's quite accurate. It's not as accurate as I would like. And I'm not sure why at the moment. It might be caused by the fact that in the Sommerfeld problem, as we know, these things don't converge very quickly at infinity. And I haven't got, at the moment, I haven't got any clever mappings to deal with slow convergence at infinity, but I'm not sure it is. Let me show you what happens in the Rawlins problem. Okay, so this is the same structure, but now it's a matrix problem. The classic one from 1975, probably well known to everyone here. Again, it's got this structure that the R plus function is just 1 over alpha minus alpha naught times a vector of known stuff. Okay, so if I put this into the library, oh, and I should say, in Rawlins' paper, he predicts, right? So he doesn't solve and then say, oh, you know, 4th root branch points appear. He predicts it right at the start from the analysis around the tip that you're going to get 4th root branch points. So I don't need Rawlins' solution to know that I should apply a mapping to get rid of 4th root branch points. I only need the local analysis that he did right at the start. Okay, so obviously you know, in a problem where I don't have an exact solution, this is going to be very useful because I'm not going to know in advance exactly what the solution looks like, but I should at least know what kind of trouble to watch out for. Okay, so this one, twice as many unknowns, and again, I've not had time for detailed analysis, so I've just picked some random parameter values. And okay, so with the power 4 mapping, so that's the one that should remove these 4th root branch points that Rawlins had. Yeah, about the same as the Sommerfeld problem, double the number of unknowns because it's a 2 by 2 matrix problem. But again, a 500 by 500 linear system is no linear system at all in modern terms. And again, about 8 significant figures. Odd thing about this, it was purely by chance that I discovered this, and I don't know why this has happened. But I was playing around with it, and I thought, I wonder what would happen if you used power 8 instead of power 4. And now, suddenly I'm getting down to machine precision accuracy. I don't know why. The power 8 mapping that I use doesn't accelerate convergence at infinity in any way. It obviously does something, because this is rather good. I mean, this is the sort of thing that I dream about, getting near machine precision in a problem like this. But I don't know what's doing that. I will give full disclosure here. I have to be honest. When I did this originally, with double precision arithmetic, one of them came out with machine precision accuracy and the other one didn't. And it turns out that seems to be down to some sort of instability in the linear system. That's something that needs further investigation. So if I do a quick and dirty thing and turn it up to quad precision to get rid of the instability, or to limit the effect of the instability, I do get machine precision. You can do the same with Sommerfeld. Going to power 4 does the same sort of thing. It increases the accuracy. I don't know why. So that's a mystery. So I'm almost done now, and I think I've gone over by just about as much as I started late. So I'm on time in some sense. So okay, so why do these double power mappings increase accuracy? I don't know. That's the next thing I need to figure out. Are there better mappings? The ones I've used are very simple. I guess there probably are. I haven't really investigated. What's the reason for this instability in the Rawlins problem? I've got a good idea why that's happening, but I haven't had time to properly investigate it. But yeah, I mean, I don't like to use quad precision. It feels wrong somehow. We should get double precision accuracy using double precision arithmetic. One last thing that I'd like to do, when I talk about all these node locations, they're not fully optimized. And it's easy to see from an analogy with a real sort of integration by quadrature. If you had something like a NAG routine, or any numerical library, and you said to it, look, give me the area under this curve, what it wouldn't do is divide it into a number of equal subintervals, and that's what the code is doing at the moment. What it would actually do is apply some sort of crude approximation, look at where the problems are, and then it would put a lot more subintervals where the function's varying more. It's quite hard to do in a case where you don't actually know what it is you're integrating, but I think it can be done, but I don't have that feature yet. So at the moment, the analogy is that the code's just effectively dividing the contour into equally sized strips, which is a rubbish way of doing it, but it's quick and easy. And then the other target, other types of Wiener-Hopf equations. So additional poles. So I said I'm only allowing one pole at the moment. Maybe if you've got an edge wave or a Rayleigh wave, you have extra poles, and of course they're different to the specular reflection pole because you don't know what the residues are at those. I'm pretty sure I know what to do with those cases. I can generalize. The one that really frightens me though is Wiener-Hopf equations that have essential singularities at infinity. It's quite hard to see. I can see how I can get this to work, but I'm nervous about trying because it's very hard. And the reason's very simple, actually, that if you have an essential singularity at infinity, it dictates to you directions in which you can and can't deform your contour. Okay, so I can't just draw these massive circles and push them out to infinity. I would have to do something, yeah, much more awkward. I think it might be doable, but yes, that's a long-term target, dealing with those types of Wiener-Hopf equation. So, final thing, there's a quick and easy way to get approximate solutions to Wiener-Hopf equations. It can be very accurate, depending on the nature of the equation. How quick and easy depends on whether I've actually written the bits of code that do the problem that we particularly need. So at the moment, anything with that sort of Sommerfeld type structure, I can just do. If there are extra poles, that's one new subroutine. I'd probably do that. But if you've got something with an essential singularity at infinity, I'm very nervous about trying that. So I haven't actually written anything up on this yet, but the various papers I've mentioned, this is the one where I used this idea to solve the problem with finite branch cuts. The Norris and Wang paper that I took my example from is QJMM 1994, obviously the classic Rawlins paper that everyone knows. And if you want to see Rawlins' problem done by the standard Krapkov formulation, which is a little bit easier to understand, I think, it's in this paper from 1995. But I'd better stop there because I've now gone over by more than I started under. So thank you very much.
Very short time because we also need.
Yeah, everyone needs coffee, I think.
Please come. Yes.
Just one really quick question about quadrature, because it's so much tied up with the cost of evaluating the function. If the function's cheap, then it's best to just don't use any weights, have a constant weight. But and I'm trying to understand your problem. How expensive is it to evaluate the function?
The expense is the inversion of the linear system, because you don't. The only way you know what the function values are when you invert the linear system that they satisfy. So the cost of doing this comes from having, you know, what did I have, like a 600 by 600 linear system.
You want to do more point, you've got to double the point. You've got to.
Well, this is the thing I was saying about nodes, that doubling is crude. I don't want to do. It's what it does at the moment because it's easy. What it should do is do it with maybe 100 by 100 matrix, which will solve in 0.01 of a second, and then inspect the solution and say, okay, you need more points here, more points there, and refine that way. So as long as you stay on systems that are less than about 1,000 by 1,000, I mean, it's basically instant, even on crummy old tablet. So there is computational expense, but it's nominal at the moment. I mean, there was someone, I was talking to somebody in the sort of group work session, and he was saying that he had this Wiener-Hopf system that was 100 by 100 matrix, and I said, well, forget it, because the number of nodes then would be so huge that it wouldn't be practical. But as long as you're just dealing with things like 2 by 2 and 3 by 3, who cares about inverting a 1,000 by 1,000 linear system?
Yes. Okay.
One comment, one question. Your procedure to factorize is some idea of what we call freedom factorization. In our case, we have an integral equation of a second kind to get factorization. In this case, since you use Cauchy integral, the operator is not compact, right? And so probably our methodology can have more convergence. We get convergence for factorization with few samples and a very simple quadrature.
It would be very interesting to compare the two. I mean, the trick here is that I'm not actually calculating the factorization.
Okay.
I'm going directly to the unknown functions.
Okay.
But it would be very interesting to see how these two compare. So I have read some of your papers. I can't claim to have fully understood all of it, though.
I think the difference is that this quadrature plus collocation on the integral on the Wiener-Hopf, and you have first integral representation, and then you're working in integral representation. You're not doing collocation, you're doing really proper integration. So this is the difference. And for that reason, I believe your method will be faster than that.
Yes. And the other question is at the beginning of your presentation. You talk about differences on computation of results for near field and far field. What's your experience on this problem? What's the difference?
I've never tried solving a Wiener-Hopf or a diffraction problem by finite elements or something. It's just something that I understand makes it very, very difficult, because you've got very intricate behavior near the tip, but you also need to get the correct behavior miles away. And intuitively, I can see that's going to be a very hard thing to do numerically, but I can't claim any experience of actually having tried it.
Last question.
Yeah, so it's back to Alexander's question about circles. So you implicitly assume that your function, let's say phi plus, is analytically continuable, at least in a certain area below, and then you have that circle. But if you have, for instance, some functions like absolute value alpha on the contour in a Riemann-Hurley problem, there is no even way to continue in by epsilon. So then that method apparently. So you work only when you have branch points, they far from each other, then you have that circle, you can then work only with the cut, but don't care about any other. So basically some kind of Hilbert method, which assumes that all singularities only the branch points.
I'm not sure I understand the question. I mean, you can certainly deal with multiple cuts and multiple branch points. If they were very close together, then it would start to break down, I think.
Yeah, I mean, if you have a kernel in a problem that has absolute value, then there is no way to have that circle.
But the one possibility which I haven't dealt with yet, so I can't get it back to full screen. But there's no necessity to actually deform the contour around the branch cuts. It's the easiest thing to do, but you could actually have two, as long as you had two contours that were reasonably far away from each other, and you're analytic in between them, it would still work, but you would start to see numerical problems if they're too close, because then the quadrature is going to fail, because the pole in the Cauchy integral is too close to the path. So, I mean, like I said in the talk, it's always dangerous to say you can do any Wiener-Hopf problem, because there's always some horrible one that's got some trap in it that you can't get past. But I think, if you did have a very nasty singularity structure, it might still be possible to do something like this, just using different contours. But I can't claim to have done it.
Okay, thank you very much again. And then